Swayam Prabha. Digital India. Educated India.
Of course, by now you have learnt where the name sigma, pi, etc. came from, isn't it? They came from these d infinity h kind of point groups, where sigma is a kind of a symmetry species, pi is another kind of symmetry species, and pi is always two dimensional. Pi, delta, these are two dimensional symmetry species. Sigma is one dimensional symmetry species. So, sigma would be the equivalent of A, B, etc. Pi is the equivalent of E, right. So, that is where your sigma bonds and pi bonds get their names from. Okay. Now, when we talk about MOs, we are going to come back to that in a little greater detail, but there are many approaches by which you can construct molecular orbitals. What is the simplest of these approaches? What is the simplest approach of constructing molecular orbitals? Yes? No, even before Huckel. Huckel is an approximation that comes later, LCAO. So, we are going to restrict our discussion to LCAO molecular orbitals. What are LCAO molecular orbitals? Right, you write the molecular orbital psi as sum over I, okay, let us say this is psi I, ith molecular orbital, sum over j, a, ij, phi j, where this psi I is the ith molecular orbital and phi j is the jth atomic orbital. Okay. So, this linear combination of atomic orbitals is somewhat like the extension of what you do in multi-electron atoms. What is the simplest approach of handling multi-electron atoms? Okay, what is an orbital? So, let us go back to that fundamental question. One electron wave function, everybody knows that by now. So, then how is it that you write electron configuration of say lithium as 1s2 2s1? Because 1s 2s, these are all correct only for hydrogenic systems. Lithium is not a hydrogenic system. So, how do you write 1s2 2s1 then? What is it that allows it? What approximation? Orbital approximation, right, where you write the wave function of a multi-electron system, multi-electron atom as a product of hydrogenic wave functions or orbitals, right. That is why you can still retain 1s, 2s, etc. Is it an approximation? Yes, it is an approximation. But why do we use it? Because the thing is, we have developed this concept of orbitals, so it makes sense to retain them to the maximum extent possible. Of course, that is only the beginning, not the end. So, what we are discussing here is also only the beginning, not the end. But then what happens more often than not is that even if you construct molecular orbitals by some other way, what is a modern method of constructing molecular orbital? Suppose you are using something like Gaussian. Okay, what is a basis set? Some functions, right? A lot of Gaussian functions, Lorentzian functions, exponential functions. You just keep on mixing them until you get the lowest energy. That is what you do nowadays. Nobody uses LCO MO anymore, unless in very, very special cases. But then if you look at these so called what is called cone sham pictures, which kind of represent the molecular orbitals. So, let us just say we can construct molecular orbitals by just mixing different functions. But then if you look at those molecular orbitals, the output, you will see more often than not you can visualize them in terms of linear combination of atomic orbitals as well with a bit of salt. The pi molecular orbitals still are above and below the plane of the molecule. Okay. So, they are qualitatively similar to what you get from LCOMO. So, learning LCOMO in great detail is not a bad idea after all. Okay, that is what we will do. And the good thing about LCOMO is that it allows us to perform a very detailed discussion, because we know everything about the atomic orbitals. We know the equation, we know the shape, we know everything. So, it is very easy for us to develop a rigorous treatment using this simplistic method, and then you can make further approximations and you can extend. Okay. And then somebody was talking about Huckel's approximation. What is Huckel approximation? Huckel approximation is that this Hij, Sij, these are non-zero only when I and j are adjacent to each other. It does not consider 1, 3, 1, 4, 1, 5, whatever. Well, 1, 5 of course it has to in case of benzene, because 1 and 5 are adjacent to each other. No, 1 and 6 are adjacent to each other. So, we will come back to that later. But before that, let us finish some unfinished agenda. Let us start with a simple system. What we will do is we will first discuss the pi molecular orbitals generated by SALCs of the cyclopropenyl group, and then once we are familiar with the method, we will get into a molecule that is very near and dear to us, and that is benzene. So, today we will discuss benzene. We will see how the energy ordering can come qualitatively, and then we will talk a little bit about Huckel approximation. On Tuesday we come back and we discuss in detail the little big brother of benzene, that is naphthalene. And when we discuss naphthalene, and by the way, when we talk about LCOMOs and all, you are familiar with the term secular equation, aren't you? Secular equation, we have actually encountered secular equations already. We will review it towards the end of today's class. So, we will see how symmetry can be used to factorize secular equations into smaller parts that are easier to handle. Okay? And all that will be discussed in the context of naphthalene in the next class. And after that, what I will do is I will ask you to do things on your own, and then we can move on to inorganic chemistry. So, to start with, let us talk about the cyclopropenyl group. Does anybody have a glue stick? I planned to bring it, I forgot. A glue stick or a stapler? Vibhav? Please, thanks. Thank you for joining us today. Okay, what does cyclopropenyl group look like? Today I have become a little wiser. Instead of drawing lines, I have brought this character tables as cheats. I am just going to paste them. What is the formula, chemical formula? Let me just write C3H3. Is there a plus sign or not? Plus sign or not? What is the structure? Triangle. Right? What? Carbon, carbon, carbon. So, if you insist on drawing your comfortable valence bond theory picture, then you are going to draw a double bond somewhere, and then you are going to write a plus sign somewhere, because it is CH, 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 right? So, if you draw a double bond, then these two CH groups are happy. This CH group is not happy. So, to make it happy, yes, you have to give it a positive charge, isn't it? And then you can do your favorite arrow pushing game, right? And you say that resonance almighty is taking place, and this is how delocalization takes place, this, that, right? Of course, we will do no such thing. So, this is, you understand what I say, right? CH, 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 there is a plus charge somewhere, and what I am more concerned about is that these p orbitals are there, perpendicular to the plane of the ring. Okay. So, let me call this phi 1, let me call this phi 2, let me call this phi 3. These are the 3 p orbitals that are going to be used to construct the SALCs, which will turn out to be the molecular orbitals, the pi molecular orbitals. Okay, so far so good. Which point group is it? D3H. So, let us have a look at the D3H character table. This here is your D3H character table, and I can cover this D3H without a prick of my conscience, because in any case D3H is written here. All right, this is the character table of D3H group. What are the symmetry operations you have? E, 2C3, this I do not know why there is a dash, there is no reason why there should be a dash on C2, 3C2, 3 perpendicular C2s, sigma H, 2S3, 3 sigma V. Where is C3? This is C3 as well as S3. Where are the C2s? Connecting an edge to the midpoint of the other side, and there are 3 such. These are C2s. Where is sigma H? The molecular plane, no problem with that. What about sigma V's? Along the C2s, right, perpendicular to sigma H, containing C2 and C3. All right. So, you understand what is what. Okay. So, what is the next step? The next step is to construct this reducible representation using these phi orbitals. Can we do that? How many pi orbitals are there? How many p orbitals are there? 3. So, this character is 3 without any problem. What happens when you apply C3? 0. They interchange, they move, so 0. What about C2? 1 or minus 1? This is a p orbital, this is plus, this is minus, this is C2, right. So, apply C2, what happens? Plus becomes minus. What about the other 2? They interchange. So, they do not contribute, only one contributes, the one on the C2 axis, and it becomes minus. So, this character is minus 1. What about sigma H? No, minus 3. It is good that we are all very positive, but some things are negative in life. What can you do? This is sigma H, right? So, it is true that the p orbitals do not change places. Right? But then because of reflection, they are going to change direction. So, it is minus 3, minus 3. S3, 0, they all move, and sigma V, 1 or minus 1? 1, right? Because this is sigma V, no change. What about these two? They change places. So, 1. If you now break this up, what do you get? What is gamma equal to? Gamma is equal to, break this up. Okay, I'll give you the answer. You have done this. What was that? Yeah, tell me. You gave me the answer, the right answer. What's the problem of saying it again? Yes. It says that it's called A2 double dash plus E double dash. E double dash. Not E dash. E double dash. Okay? So now what am I supposed to do? What I am saying then, there's the symmetries are A2 double dash and E double dash. So I have to use the projection operator of A2 double dash and E double dash, and I am going to generate the SALCs, right? But before that, I know something that will simplify my life a little bit. What is that something that we learned yesterday? What did we learn yesterday? Descent of symmetry. So what I am going to do is, instead of using this full D3H group, I am going to use a subgroup. Which subgroup should I use? C3. Just C3 is enough. Nothing else is required. Because see, the point is, only axis of rotation Cn with n greater than or equal to 3 are going to cause mixing of orbitals, isn't it? What does C2 do? C2 is 180-degree rotation, so each orbital remains just itself or becomes minus, or sometimes x and y mix if there are no x or y. But if it is more than 2, if it is 3 or more, then definitely orbitals are going to mix. Okay? So it is, that is the subgroup that we should work with. So what we do is we focus on the pure rotational subgroup C3. We are going to work with C3. That is a rule of thumb. Work with a pure rotational subgroup, because it is the rotation with respect to Cn with n greater than 2 that is going to really cause the mixing of orbitals, and it is the easiest to approach the problem by using a rotational subgroup. Okay? So here we use C3, and you see life has become so simple. Right? What do you have? You only have C3, C3 square and C3 cube, that is all. Right? The only problem is that life has become simple, but in that process life has become a little complex also. You have complex quantities here. But then we know how to handle complex quantities. Is there a question, Nishit?
So in case of say an octahedral molecule, we preserve the C3 and the C4, and we only preserve the axes that are higher than 3.
Yes.
We preserve all of those.
Equal to or greater than 3. We are doing the same thing here. Because the same logic is there, that you cause a mixing by using this rotation axis. Okay? Fine. So, but then we know already what is epsilon, what is epsilon star, right? What is epsilon? It is even written here, e to the power 2 pi I by 3. What is that? Square root of 1, isn't it? Cube root of 1. Square root of 1 is too simple. Cube root of 1. And if I write it in the trigonometric form, what would it be? E to the power 2 pi I by 3. In trigonometric form, what would it be? Yes, so we are going to use that form eventually. Alright. So now rest is simple. You can just use the projection operator of A. Okay, what is the correlation? A2 double dash becomes A, is that right? Let me cover everything other than what is relevant. I don't need this. I don't need this also. This is the only thing that is required, isn't it? Because 2C3 is basically C3 and C3 square. I mean, only wish I brought some cardboard instead of paper. So, what does A1 dash become? So, you have to read the character of C3 twice, right? If you want a correlation between D3H and C3, you have to read the character of C3 twice, because here we have written C3 and C3 square separately. They do not belong to the same class anymore. So, A1 dash becomes A, A1 dash corresponds to A, A2 dash corresponds to A, A1 double dash corresponds to A, A2 double dash also corresponds to A, right? Right or wrong? Okay, what about E dash? What is epsilon plus epsilon star? Can you work that out? Write in a trigonometric form and work it out. What is epsilon plus epsilon star? What is epsilon? Tell me, cos? Yes, it is -1. But let us work it out so that we all understand. What is the trigonometric form? Tell me, epsilon? Cos 2 pi by 3 plus iota sine 2 pi by 3. And what is epsilon star? Cos 2 pi by 3 minus iota multiplied by sine 2 pi by 3. Okay. So, when you add them, what do you get? -1. Are you all convinced that it's -1? Okay, you subtract, what do you get? So, if I divide that by I, then again it becomes a, then again I can get rid of this. Does that remind you of something? You add once and you add two imaginary numbers, two complex numbers, and get a real number, and then you subtract one from the other, divide by I, you get another real quantity. Have you done that somewhere? P orbitals, remember? P plus P minus gives you Px, P plus minus P minus divided by I gives you Py, right? We are using the same technique here, nothing else. Okay. So, if you are a physicist, you do not need all this. You can just work with the expressions. You do not care about figures. We chemists like to draw figures and like to work with figures. That is why we have this inclination of converting all imaginary quantities into real quantities by adding and subtracting, divided by I wherever, multiplying by I wherever required. Okay. So, epsilon plus epsilon star is -1. So, now tell me what is E dashed? E dashed is just E, isn't it? You just add these two. Do not forget that E is not really a reducible representation. Huh? One epsilon epsilon star is a reducible representation, one epsilon star epsilon is another reducible representation. They are taken together and they are called E, that is all. Okay. So, E dashed here becomes E. What about E double dash? That also corresponds to E, same thing. Are we clear? So, in C3, what will I write? This is correct in D3H. In case of C3, what will I write? I will write A plus E when I am working with the C3 subgroup. Okay. So, now see, let us use the projection operator A on phi 1. What do you get? Character tables are there in front of you. Now, you should be able to work out, and also we are working with only this small character table. E operating on phi 1 is phi 1, that multiplied by 1 is how much? Phi 1 plus C3 operating on phi 1, what is it? Phi 2, multiplied by 1 is phi 2. Then C3 square operating on phi 1 is phi 3, that multiplied by 1 is phi 3. So, this is the SALC that you get of asymmetry belonging to symmetry species A. Because when I say of asymmetry, then our organic chemistry background might interfere. It is not asymmetry, asymmetry. But just to make a point, what you could do is to check here, can you go back to D3H point group and use the projection operator of A1 dashed on phi 1 and satisfy yourselves that you still get phi 1 plus phi 2 plus phi 3. A2 dash, sorry, A2 double dash. When A2 double dash operates, do you still get phi 1 plus phi 2 plus phi 3 in D3H, not in C3. And while doing that, do not forget these coefficients. And do not forget that C3 and C3 square are going to give you different results. That is the easiest way of going wrong. C3 phi 1 is phi 2, C3 square phi 1 is phi 3, do not forget that. Phi 1 plus phi 2 plus phi 3 it's coming, right? Yeah. What about C2? 3 C2s. This C2 operating on phi 1 makes it minus phi 1. The second C2 operating on phi 1, what does it do? C2. Yeah, minus phi 2 minus phi 3, right. Then sigma h minus, then S3 minus phi 2 minus phi 3, then 3 sigma v's, I think it will be sigma 1, sigma 2, sigma 3. Okay. So finally you get the same answer. It's just that the coefficient, yeah? What? Yeah, if minus is there is no problem. It's just a constant, right? If minus 1 comes out, it's fine. As long as right. So please do that. Do that and see what you get. I completely forgot to do that. So some signs will change and then see what you get. Got it? So you get something multiplied by phi 1 plus phi 2 plus phi 3, right? So that's what it is. Now, what will be the normalization constant? Root 3, 1 by root 3. So I hope everybody is convinced that when we, no matter whether we work in the full D3H group or whether we work in the C3 subgroup, at least for the first one, for the one dimensional representation, we get the right answer. Okay, work it out, it will come. Now, the advantage of using the subgroup comes when you are working with the two dimensional representation. Because now what we have done is, we have essentially broken down the two dimensional representation into E1 and E2 or EA and EB, whatever you want to call it. Okay. So next is, let us use the projection operator of E1. What is E1? The first line of 1 on phi I, phi 1. What do you get? What do you get? Tell me. PE1, 1 epsilon epsilon star on phi 1. Phi 1 plus epsilon phi 2 epsilon phi 3 plus epsilon star phi 2, doesn't matter what you write. What do you get when you make PE2 operate on phi 1? Because you told me. It doesn't matter. Actually, I got it to be phi 2. Depends on whether you are rotating this way or that way. It doesn't matter. So, phi 1 plus epsilon star phi 3 plus epsilon phi 2. Okay. Before going any further, I would like to draw your attention to what is going on here. By using this rotational subgroup, we are actually generating a linear combination of atomic orbitals, right? Because you rotate once, you get phi 2 from phi 1, you rotate twice, you get phi 3, you rotate thrice, you get back phi 1, and you are doing all these rotations. So, no matter what you do, you are going to get a linear combination of atomic orbitals, you are going to get the MOs, right? And you can say that these are the MOs and be happy about it. But the problem is, if we leave it here, there are two issues. First of all, how do we justify that these are the MOs for the cyclopropenyl group? The cyclopropenyl group, there is no character that is epsilon or epsilon star. So, we should go back to D3H group. And secondly, we do not really want imaginary coefficients. How will I get back to D3H group? How did I get E1 and E2? By splitting E double dashed, isn't it?